Live in 3, 2, 1.
Hello, and welcome to this edition of SparkFun Live. We are live here. I am Dave Stillman, your host, and
Ben Leduc Mills.
Dr. Ben Leduc Mills. Today we are going to be talking all about balancing robots. Balancing robots, like this little guy we have in front of us, are the classic inverted pendulum computer science-y type problem. It's an inherently unstable platform that we try to make stable by spinning some wheels. So there's a lot of really complex stuff going on. There's a lot of complexity in this problem. You see this guy is about to fall off the table. We won't let that happen. But yeah, so we're just going to be talking all about self-balancing robots, kind of some of our successes, our failures, what we've learned along the way, and hopefully you find it a little bit educational. Hopefully you learn something. Lifelong learners, hopefully we all learn something every day, right?
Indeed.
Cool. So, with that, start off with this. I think this is a new product. I don't know if we're allowed to talk about this yet, but it's we call this the MIP. This is a consumer electronics, I would say toy, but it's so much more. It's like one of those really, really smart toys, right? So this is MIP. This was designed, I think, at UC San Diego at their robotics lab there. And it's designed to be just a kind of fun little playful, hackable, self-balancing toy. So it's got a lot of technology packed into this thing for, I think it retails for 99 bucks. So you can see there's like a little gesture sensor. You can push them around. Hope he doesn't fall off the table.
Yeah, he won't.
But like I said, there's a lot of tech packed into this little dude. So inside there's also like a Bluetooth module, so you can actually pair it with your smartphone, use your smartphone to drive this thing around the table. It actually dances, it'll analyze and figure out the beats per minute of your music and kind of dance along, you know, hopefully nobody's making a gif of this, but it'll dance along with your own music or has some built-in stuff. It gets a lot of fun when you get more than one of them. You can actually play sumo and stuff and see who can knock over each other's robot and whatnot. Overall, a really, really fun toy. In just a couple of minutes, we're actually going to be taking this off, taking this apart. We're going to be taking the back cover off and taking a look at what's inside, what makes this little dude tick. But first off, I want to see what we can stack on it.
Yeah. So it comes with this little kind of attachable platform, and the balancing aspect of this MIP, which actually stands for Mobile Inverted Pendulum, in case you were wondering. So you can actually adjust the center of gravity so that it can account for added weight. So let's see if we can't make it fall over.
I've got a roll of tape here, not super heavy, but if I put it right on top, whoop.
It can even roll over circuit boards.
Yeah, roll over a little motor driver. So you see how it dynamically kind of adjusted its internal system. Back up. It adjusted its own algorithm internally, so it figured out, oh no, like my center of gravity is now a lot more forward than it used to be, and so now it's still balancing just in place. Let's back them up a little bit. So it sees when it's going that far forward that it says, oh, inside. It's like, I need to figure this out again. So it kind of readjusts. It finds a new center point, even though the center of gravity is shifted. That's really key. Turns out to be a non-trivial problem to solve. And we can get really fun with this. I don't want to put a glass of water on it. Phone, I don't know.
Oh gosh.
How many iPhones can MIP hold?
0. Also, if you have any questions or comments for us, you can post them in the comments on the YouTube channel. So feel free to do that, and we'll do our best to answer them live.
We'll do our best.
Oh, yeah, and we're in production, which is the downstairs area of our building here in Boulder, Colorado. Just off screen to the right of me is one of our Reflow ovens. Some of our manual techs are behind me, along with some of our dogs. So you may see them wandering in and out, happily wagging their tails.
This is kind of a non-traditional SparkFun Live. If you're familiar, if you've tuned in with us before we were in our classroom, which is a lot more set up, it's a lot more geared to be an actual studio. So you can see here, it's not exactly, you know, it's not exactly studio-like in here. There's a lot of compressed air going on. We've got a pick-and-place machine going on right behind it. It's, you know, this isn't really typical. We're doing this for a couple of reasons. One, this is the last SparkFun Live at this current building. If you don't know yet, we are actually moving buildings, right? So we're going to be about 2.5 miles north of here for our next SparkFun Live. So tune in again. But just kind of as a nice send-off, we decided to change up the venue a little bit, actually have it in our production floor, just to give you a sense of what we do here. A lot of people don't realize how, like, you know, we're kind of a big company now. We're 150 some odd people last I counted, and there's a lot going on in this building. So we thought we'd show some of it off, you know, before we leave this building forever. I'm gonna miss this place. So with that, I think I broke the MIP. It doesn't balance anymore. Oh, you make it balance.
It likes me.
So we just wanted to show this thing off, one, because it's a new product. You'll probably see this on the storefront, I think later this week, maybe on the Friday new product post with Rob. But we thought we'd show it off, give you a little sneak peek of what's coming up, and just to show off just the tech inside of this. We'll take it apart and talk about it a little bit more later, but this is really cool. I know firsthand, because I've tried to build a couple of these self-balancing robots. They're not easy to build. So with that, I'm going to see if I can turn this guy on, see if I can get him to balance.
Excellent.
And, I don't know, see if you can stack stuff.
Yeah. So Dave mentioned that the MIP has a mobile app. I'm going to try to get this guy going with my mobile phone here. I don't know if you can see that, but it starts off with a drive mode. So you can actually manually drive this guy around. Ooh. Very sensitive, but you can do it. You can spin, right? But also, there's little cans, they call them cans, which are basically like little emotions that you can load into them. So one of my favorite ones is you can make him sleepy. So let's find sleepy here. So. He's snoring if you can't tell. So that was an error. He falls over. And it's pretty cute. How you feeling over there?
I don't know, we'll see. Give me 2 more seconds.
Okay.
Maybe 30 seconds.
There's also a neat dance mode. Let's see if I can get him to dance. And it'll actually prompt you to pick a song from your own phone's iTunes library. So, let's see here. Oh, okay. Maybe we won't do that actually. But the idea is that you can kind of tap along and then, the MIP will dance. Actually, there's a different mode where we can make him dance in anyway. Let's see. It's actually pretty cute. So you can switch modes by just turning the wheel here. All right, let's see.
It's going to get attacked by a dog here pretty quick.
So now, the internet has seen me doing that, which is great. So he's pretty funky. He gets down.
So cool. I guess I can talk about this if you want.
Stop playing. So yeah, take it away.
So yeah, this is a very unstable robot that I built. You can see it's a little skittish right now. Something happened. I think I bumped off the center of gravity, so it doesn't know its center point anymore when I was moving it. You can see that it's sort of doing a decent job of balancing itself. So this is all controlled with an Arduino Pro Mega, and it's got a couple of optical encoders on it. So, and some pretty fancy software that hopefully lets it stay up. Like I said, it's not the best right now. It's had a few. I don't want to say major falls, but it's seen its share of development. So when I rebuild it, it will be much stronger, faster, better, more balancier, right? So this is just kind of a platform I put together because I wanted to explore balancing robots because I think they're really cool. So I put this together using a bunch of Actibotics stuff. So I'll set it down here and we can take a look at what's inside. Step 1, unplug it.
Yes.
So a couple of things to note. So like I said, so this is all put together using Actibotics stuff. This is the extruded aluminum kind of channel system that we started carrying a number of months ago, about 6 months ago. And so that's the frame. It's about 24 inches tall, about 2 feet tall. And at the base, it's got these drive motors. These are 90 RPM drive motors. They're geared down. It's a good mix of fast and slow. They're not too fast, they're not too slow. Really precise control, which I like a lot. Turns out they're not quite fast enough, so as the robot leans past about 10 degrees or so, they can't keep up and it won't actually recover from it without completely falling forward. Kind of a bummer, but it is what it is. Down below here, if you look, super small, you can see there's actually some timing belts right in there. And I custom laser cut a gear that would run up against that timing belt up and all the way up through the channel here into this optical encoder. So these optical encoders are available on our website. They're kind of expensive. They're like 40 or 50 bucks or something, but they're super, super high precision. I think there's 1,024 clicks per revolution, and it turns out to be quadrature, so it's like 4,192 clicks per revolution. Plus you get that directionality, so you can detect which direction the wheels are spinning. So there's a really, really tight linkage between the drive motors and the wheels and these optical encoders here. So you see as I spin the wheel, you see the optical encoder spinning up there as well. So the guts of this whole operation here are this guy. So this is an Arduino, I think it's a Pro Mega that we sell. This is an Arduino clone that we assemble here in-house. And so it's just like the Arduino Mega. It's based on the Atmega 2650, 2560, whichever one that is. So it's got a lot of I/O, a bunch of interrupts, which is what I was looking for the optical encoders to be able to read quadrature on 2 channels. And the motor driver here is a Monster Moto Shield for the Arduino. So this is something like drives 30 amp motors, way overkill for this project, but I like the form factor. It's a shield, sits right on top. Can't really complain. In addition, we have this little XP Pro here. So this is just a Series 1 XP that I have linked up to my laptop. It spits out a bunch of debugging information. I'll talk about this in a second, but debugging information on a project like this is so crucial to be able to know what is going on inside the brain of the Arduino. Like what values, what's the value of what's the output of the inertial measurement unit? Oh, is the accelerometer, sending unfiltered output or something? It's really nice to know that. A couple of late additions to this project that you will definitely want if you build something like this are a switch. So this switch, this big missile cover switch here, is linked directly to the power supply for the drive motors, right? So it's really nice to be able to kind of play with the thing, move it back and forth without having the motors actually turned on and having this thing run all over the house. Like I said, it's already fallen over more than a couple of times. Several of the pieces are duct taped together, but it is really nice just to have, it's kind of a kill switch. So I don't want the motors on, flip it off, and do all the debugging. Like I said, that was kind of a late addition. I'm not a very clever man, so but it turned out to be super useful. So one last thing I want to point out here, well, I guess one more thing on the backside, are the batteries. So these are the batteries. So these are 2 7.4 volt LiPos. They're big, high capacity, something like 2200 milliamp hour, really big. So and I have them wired together in series, so I actually get 14.4 volts or 14.8 volts out of them to drive these 12 volt motors. It's a little bit more than the motors are rated for, but most motors, there's a lot of tolerance in them. The reason I have the batteries mounted so high, they're right at the top. In this whole frame, they're mounted right at the top of the chassis. The reason is I want the center of gravity of this whole thing not to be low down here. There's already a lot of weight at the bottom. There's all the motors, all the wheels, all that stuff weighs quite a bit. What I want is to move the center of gravity up. Right, so by having the batteries up here, it makes it a lot easier to have something to act against. If you drew a free body diagram and think back to physics, where's the center of gravity of this? Probably right about here or so. So when the wheels move back and forth, what they're acting on is they're kind of like pushing up against the body of the robot itself. So the higher you can move that, the easier it is to actually balance. It's kind of non-intuitive, but like having the higher center of gravity makes a balancing project a lot easier. Oh gosh. So this is our reflow oven. This is birth of a SparkFun widget. What do we have here? Looks like a it's an electric imp breakout shield. Look at that, or breakout board. So you're actually watching live for the very first time, birth of a SparkFun widget. You get to watch it come out of the reflow oven. This board has already been through the pick and place machine. It's fully populated. It's got all the components on it. What it's coming out of right now is the reflow oven where all the solder is melting. And there it is. It's a whole panel of electric imp breakout boards. So that's literally hot off the press, fresh out the oven. They're beautiful. Watch out, they're super hot. So like I said, we are in our production floor. So this is real. If you buy an electric imp in the next couple of months, chances are you just watch it roll out of an oven. Isn't that cool? Man. Gives me the warm fuzzies. We just had a big milestone about a month and a half ago or so. We built, per our system, whoever programmed that, we built our 4 millionth widget since 2007. I think we started keeping track of that thing, that sort of number. So yeah, our 4 millionth widget. It's a lot of widgets.
It is.
So one last thing on the back of this robot. So, like I already showed you the kill switch to turn off the motors. One more thing, this is, like I said, been duct taped on a couple of times. You see there are 4 potentiometers here. When I talk about the control system, the actual loop that's controlling this to try to make it balance, these are really, really crucial. And it took me a long time to figure out that, wow, having a physical interface to a machine like this turns out to be really, really useful. Just throw as many buttons, switches, potentiometers on as you possibly can, because it makes it a lot easier to debug something like this. Rather than having to change a value on your Arduino code or in the IDE or whichever programming environment you're using, you don't have to, oh, what if I bump that from 22 to 27? What effect will that have? Recompile the code, re-upload the hex file, plug it in, unplug, there's a whole process there. It takes about a minute. It's really nice to just be able to tweak something on a knob and just say, okay, 22, 27, and watch the output in real time. See how that affects the control loop. That turns out to be really, really, really useful. So one of the first things I did when I made the miniature version of this balance robot is put the 4 potentiometers on it as the 4 tuning parameters for this control loop I was talking about. So I think...
What's on your computer screen?
That's a great question. Let me see if I can turn this back on again.
Okay.
So in addition to having a physical interface, like having knobs and switches, it also blew my mind how useful it was to have a physical output that you could look at on a computer screen. It turns out humans are really, really bad at numbers. So if you've ever seen like a big Excel spreadsheet or something like that, turns out to be not very useful at all, unless you can interpret that data into something that your brain can figure out. So let me restart this, get a fresh screen. So this is a little processing sketch I put together. All of this is available with the code that we'll go over on GitHub. And this is a real-time graph sent over the XBs, the wireless link, as to what is going on the robot itself. So like I said, there's a couple of things that are controlling this algorithm. One is an inertial measurement unit. It's measuring which way is down, essentially. It's a little bit more complicated than that. We'll talk about it. But as I move this robot back and forth, you'll see, looking at this graph right here, see how it changes? It's going up and down, that kind of sine wave. There's something else talking over top of it. But so that's actually the position of the robot, what it thinks it is, which way it thinks is down, right? So it's reading how many degrees off it is from center, whether it's +3, -3. If it's more than about 10, it's going to fall over, like I said. So it's really, really useful to have that real-time graph. So you can see, as I move it, watch in real time. Look at how that changes. Look at what's going on. Like why did it behave that way? Oh, it turns out there was a big spike in whichever graph. Oh, that affected the algorithm in a really unexpected way. It makes it a lot easier rather than looking at the flow of numbers. If we go back to the processing, you'll see down here, this is actually what the numbers it's plotting are. When I look at that, I can't get any useful information out of that, right? So it's really useful to take those numbers and put them into a nice graph that I can see what's happening as I move this. So yeah, like I said, I'll talk about this. There's 2 graphs here really quickly. This one is just the position, right? And then the one down below here is actually the derivative of the position, right? So it's actually showing how fast it's changing. So if I jerk it really fast, this one only bumps a little bit, but down here you'll see a big spike because the actual position is changing really, really rapidly. So that's just the derivative. That's the slope of this line is graphed in magnitude down on the second graph. Cool. All right, so like I said, as many graphical representations as you can. I don't care what it is, if it's an LCD screen, if it's a processing sketch. Literally, I went on to the internet and searched for graph processing org, and the first result was this dude who had a nice, plot 5 things on one line graph, and it turned out to be really, really useful. I totally blatantly stole that code, adapted it for this use, and again, one of the most useful things that I put together.
Hey Dave, what's
Yeah.
processing?
Oh, what is processing? Oh, whew, asking the tough questions. That's a good. How about you answer that one?
All right.
You got more of an elevator speech for this one than I do.
I don't know. Well, processing is a free open source. It's both kind of a language as well as a coding environment. It was designed by Casey Reese and Ben Fry at the MIT Media Lab, and it was really designed for artists and people that were unfamiliar with code but really wanted to do something visually creative and interesting without kind of having to dig into lots of crazy amounts of code. So we use it a lot here at SparkFun for things like visualizations, and it talks to Arduino very nicely, so you can do things like Dave did with reading sensor values over XB wireless.
I find it is a lot of programmers, kind of by trade, laugh at it a little bit. It's not real programming. but as a programmer by trade, it's so useful. If you've ever done any graphics programming by hand, it's awful. Targeting all different platforms, writing things for, oh, is it OpenGL or is it direct? Like, yeah, it doesn't really matter. Processing abstracts all of that away. So to draw a graph like that, I think that whole sketch is less than 100 lines of code. So it's just drawing a line over time. There's a little built-in delay function. So as it gets new serial data, it just plots it. I don't want to say it's super simple because it might be a little bit more advanced, but if you have any background in the graphics programming, you'll look at this and be like, whoa, it's revolutionary. Makes really complex tasks seem pretty trivial.
Right, and it actually ships with a serial library. So you don't have to worry about connecting to hardware and writing that whole thing yourself. It's really just a couple lines of code after you import the library, and bam, you've got access to your serial port.
It's one of the things I love about, especially Arduino, microcontrollers in general. Everything speaks serial. I do a lot of web programming. I love Python. I love Ruby. I love all of these different languages, and all of them have a serial library that's really easy to interface with.
Also, if you're into processing but haven't kind of checked back with the community for a while, they just released this thing called P5. And this is built from the ground up in JavaScript. So if you're more of a web developer person, but you're curious about hardware stuff, or even just doing more visual stuff with HTML5 and JavaScript, check out p5.js. I think it's p5js.org. Very cool. I've been messing around with it. Right now I'm trying to get it to talk to our data.sparkfun stream. So check back on the website later. I'm going to have that working.
Shameless plugs. We love it. So that robot I just showed you, that really tall one, the 24-inch tall, self-balancing sort of robot, turns out that was really expensive to build. I'm lucky enough, I'm fortunate enough to actually work here at SparkFun, so I got all the parts, kind of at a discount. But even then, it cost a lot of money. All the Actibotic stuff, it's a lot of aluminum. That motor driver was super expensive. All the Arduino Pro, all these different bits and pieces cost a lot of money. So a couple of weeks ago, when I first, heard about SparkFun Live and getting to be in front of the camera, I thought, what if we could take all the concepts from that and kind of shrink them down and make it a little bit more affordable and, a little bit more fun to make a self-balancing robot. Turns out it's really, really, really tough to build self-balancing robots, especially shorter ones. There's a lot of physics going on. So that actually, as it turns out, the taller the robot is, the easier it is to self-balance. Like I said, there's all that mass up top to kind of act against. Bigger wheels. There's a lot of physics. So I tried to build a smaller one. It didn't work nearly as well. It actually doesn't balance right now. But I'll go over what I did and show you some of the trade-offs I made with building this miniature version. So as you can see, next to, I wish I had a banana, but here's an iPhone for scale. So it's a little, maybe an inch taller than the iPhone, and it's all built with cost in mind. So I used, at the top here, let's start from the top down. At the top, you see I use this all-in-one 9-DOF inertial measurement unit. So this is a built-in, it's got 3-axis accelerometer, gyro, and magnetometer. I'm not using the magnetometer for this application, but it's there if you want it. I got a barrel jack connector so I can plug in the batteries, which are on the back. Again, you want that center of mass as high as possible, so I mounted the batteries all the way up at the top. The guts of that we'll talk about in a second, but the whole frame of this thing is just a piece of proto board. This is one we saw on the website. It's really nice, thick proto board. I don't know what the thickness is, but it's got a nice heft to it. So I decided, just put everything on that. So I think it's called the Wombat if you look it up on our website. So this is all just proto boarded together. You'll see down below, between all the mess of jumper wires, there's an Arduino, it's a Pro Micro down there, which is kind of the all-in-one. There's no FTDI board on, or no FTDI breakout necessary. You can just plug it in over USB to a laptop and program it. Super useful. The only downside with those boards, or these boards, are that USB connector. It's a surface mount connector, and it's designed really well for lateral insertions of a micro USB cable. But as soon as this thing started falling over more than a couple of times, it pulled up on that connector. So you can see here, I don't know if it's possible to see on the video, but there's a lot of hot glue. So I resoldered, the thing fell off, I put it back on, I hot aired it back together, and then I put a little dab of super glue and then a lot of hot glue on top, just to kind of ease the stress of that connection. So, pro tip, right? So moving further down, again, ignore the mess of jumper wires. I really like jumper wires a whole lot. They make my life a lot easier. Down here, this is a tiny little, this is actually a dual channel H-bridge. So I forget the exact model number, TB6612FNG. It's a dual channel H-bridge, trust me. I think it runs like $9. up to, I think, 1 amp per channel. So much more suited for an application like this. It's a much smaller robot. I don't need 30 amps per channel. These are tiny little motors. I think they draw at most 300 milliamps, so I'm not too worried about it. Down at the bottom, that's a previous iteration when I used the 6-off. We don't have to talk about that. The motors and wheels that I'm using are actually from a company called Pololu, and they're really, really fantastic. I love Pololu. They're a great little company. And you can see here, there's the motor here going into a gearbox and this plastic enclosure. I wish I had one of these taken apart, because on the inside here, it's nice to have this all-in-one case. So inside there, you can see there's 2 little IR emitters and detectors and some little tiny potentiometers you can use to adjust those. And as I spin the wheel, you can see there's those little notches in the wheel itself, the little white wheel. Not the tire, but the wheel itself has notches. So as I move that, it passes in front of the IR emitter and detector out of phase. Right, so you can actually get quadrature output from this. And again, quadrature is that the output that you can see, and you can tell based on how many clicks there are per second, you can tell how fast the wheel is going. And since these 2 are out of phase and there's 2 sensors, you can actually tell which direction the wheels are spinning as well, which turns out to be super useful information, as we'll talk when we get into the algorithms of controlling these sorts of things. So it's nice, 2 wheels, 2 encoders, super simple. And like I said on the last robot, the first thing I did when I built this is add these 4 potentiometers, right? So these are the 4 control tuners for the coefficients of this PID algorithm that we're going to use to control this robot. Again, this one doesn't work. I could plug it in. It would probably drive off the table, but it is a good demo for how the control algorithm works. So I'll plug it in just a second. So
We're going to talk about each of those 4 tuning algorithms,
we certainly are. So, oh man, PID, where to even start?
I don't even know.
PID, what does it stand for? PID, this is like the classic control algorithm. The PID algorithms are inside all sorts of really, really strange appliances, but it is the classic control algorithm for an inverted pendulum or a double inverted pendulum, if you want to get really crazy. I don't even know if triple's done yet, but I'm sure someone out there figured it out. I'm having enough trouble with one axis and a single inverted pendulum, so I'll leave it at that. But the PID algorithm is, at its heart, pretty simple, but it's got some complex implementations. At its heart, so it's positional, I think, positional, integral, and derivative. So it takes these 3 kind of inputs into this function and spews out one output that it feeds to a system that then sends its output into the PID again. So it's kind of this control loop, right? So in this case, we have an inertial measurement unit, which we'll talk about that in a second, but it hopefully gives you a really, really clean output of which way is down or how far off of center you are. So, if the robot is straight up and down, it'd be nice to just have a 0 reading. As it leans forward one way, there's a little accelerometer inside that chip that will detect that and give a proportional reading that says, oh, hey, now I'm 1, 2, 3, 4, 5, 45 degrees out of phase, or minus 45 degrees out of phase. Do the wave. Too much, too less. So hopefully that output is really clean. You can put that into the PID controller. And the first thing is the P, so just the position. So if it's off by 45 degrees, that would be your P. That's the P in PID. And then the D, let's do the D next. So the D would be the derivative, right? So that's what I showed you in the graph. So it's the kind of how fast it's changing. So if you are at 45 degrees and not moving, because maybe the motors are going really fast, then that D is going to be 0, right? Because there's no acceleration. There's that graph is going to be at 45 degrees. There's no amplitude to that graph, right? And the integral is the kind of the sum of that error over time, right? So it's kind of, imagine if you shaded in the derivative of the graph. It's been a long time since I've taken calculus. Forgive me for butchering it. But so with those 3 components, you can put those together, kind of fuse them all, and get one output out, right? And so the 4 tuning parameters, these are actually tuning coefficients. It's actually pretty simple math, but it's tuning these coefficients in front of the P, I, and D values. So it just adjusts how much of an effect those have on the algorithm itself. Pretty sweet.
Very.
So, oh man. Turns out it's not super simple to get output out of an inertial measurement unit either, right? So this IMU, the little 9DOF chip, in this one little chip, I don't know how they do it. Pretty sure it's magic, little pixie dust. They throw this together, and inside the tiny, tiny surface mount chip, there is a 3-axis accelerometer, a gyroscope, and a magnetometer. So for this application, we're just using the first 2, the accelerometer and the gyroscope. So the accelerometer can actually detect which way is down. Right, so it's in 3 dimensions. No matter which way this thing is oriented, it's measuring acceleration. Right, so if I hit it from this side, it'll tell me, oh, there's something bumped me from that side, or the top, or the bottom. A nice kind of side effect of all of this is it is actually measuring the force of gravity. So that's the force exerted onto us, everything, by the Earth, and it can actually measure that. So that's how it knows which way is down. So as I turn it, in 3D space, it's actually measuring which way the Earth is pulling, right? So I don't know how it does that. Like I said, pretty sure there's just magic inside. But so it knows which way is down all the time. Mostly we only care about in one axis because it's it only is going to fall one way or the other. But yeah, so we're measuring which way is down. The other cool thing on that chip is that gyroscope, right? So that is measuring how fast it's rotating. So if we rotate it really fast, it's going to give a really high reading. As it stops, it's going to give a reading of 0. So it's there's no rotational movement at all. So with those two things, we can fuse those together and get a really nice reading. Question is, why do we have to fuse them together?
Good question, Dave. Why do we?
But wait, there's more.
Oh, wait.
I'm going to draw a picture and show you why. So hypothetically, if I just move this back and forth and back and forth, the graph of which way gravity is pulling would look something like a pretty nice sine wave, something like this, right? So that would be the output graph if that was your 0 axis, your x-axis, if you will. So if it would just look like that, just moving one way or the other or the other. So the output from the accelerometer, as it turns out, is super, super useful, but it's really noisy, right? So there's a lot of kind of error in it. As this thing moves, the sensor itself has a lot of kind of, you might call it jitter and noise. It's not going to be a super clean output. So the output from the accelerometer, if we were to graph it on the same axis, would look something like this. So you can kind of see it sort of matches the curve. It's giving valid output, but at any given point, let's say I'm hard over, I'm leaning 45 degrees in one way down here. What if it takes that reading? That's going to be way off, right? So it's a really noisy output, and you can't really trust it. So the easiest way to get over that kind of limitation is, you might say, to filter it. So have some kind of low pass, maybe a time-based filter. But the downside with that is the readings that you get that are clean and filtered are going to be a little bit delayed. There's going to be a little bit of lag. So it's not going to be an instantaneous real-time reading, right? So that seems like, well, you kind of need it. I need to know how far over I'm leaning right now to be able to compensate for that. So what do? That's where the gyroscope comes in. So the gyroscope is, like I said, really, really cool. The neat thing about the gyroscope is it's got a really clean output, unlike the accelerometer. So the gyroscope is going to have a nice clean graph that's going to kind of mimic the line, but the downside from the gyro is it drifts over time. So the first maybe 10 seconds of your robot balancing, it's going to be, oh sweet, it's going to tell you exactly, how much the error is, how far it's leaning in either direction. But after maybe 10 seconds, 15, 20 seconds, a minute, 2 minutes, 5 minutes, 10 minutes, it's going to be way off because it doesn't have anything to kind of give it a reference. So it knows, hey, I spun that much, then that much the other direction, but every time it moves, it's going to be off. It's going to accumulate this error over time. So, if I move this, if I flip it back and forth 10 times, the gyroscope's going to give really valid output until it drifts. And so that way, maybe by the 10th time, it's going to be completely out of phase. So if I were to graph that, it might look something like this. So it's going to follow the same curve, but see how it chases it a little bit, so it's not quite in sync. Right? So it's going to drift over time. So what we need is a way to put these two things together. Right? So there's a ton of different algorithms that do this. The most popular one by far is called a Kalman filter. If I knew the first thing about Kalman filters, I would love to teach you all about them, but I just don't. It turns out linear algebra is super, super difficult, and it varies implementation to implementation. Every different inertial measurement unit that we sell or anyone sells is going to have a little bit different kind of output, input to the Kalman filter, a little bit, different coefficients to tweak to make it actually give valid output. So that's why we let people on the internet do all the heavy lifting for us. So for both of these robots, I kind of relied on some open source code, which turns out to be super useful, right? So the first inertial measurement unit I played with is our 6DOF inertial measurement unit. So it's the 6DOF digital IMU.
Hey Dave, what's DOF?
Oh, a DOF is a degree of freedom. So when I say 6DOF, I mean that it's got that 3-axis accelerometer and the 3-axis gyroscope. Oh. So each axis is 1 degree of freedom. So if it was a 1-axis gyroscope, it would only be able to tell which way it's facing this way. If it was a 2-axis, maybe this way as well. Then 3-axis, it's got all 3D space.
Oh.
So generally, the more DOFs, the better. It's kind of related to like a robotic arm that has several degrees of freedom. If I have a robotic arm that can only move one way, that's one DOF. Yeah, but once you get into like 5 DOF, 6 DOF robotic arms,
there we go.
My arms are like end DOF, so I could just, scary. So the first board I played with, as I was saying, was the 6DOF inertial measurement unit. It's a tiny little chip down here. You can't see it. It's really tiny. It's a little development board that has 2 chips on it. So it's got discrete chips for the accelerometer and the gyro. And then it outputs all of its data over I²C. So that's this little guy at the bottom, right down there. Let's see if you can get a little bit more offset. So this guy right here. So that's the 6DOF development board. There's a great bit of code out there that does that fusion algorithm, that Kalman filter for this piece of hardware, for the 6DOF digital board. And it is called FreeIMU. There's a ton of code. If you look in the description of the YouTube video, there is a link to, I think, the project code here. Some of it uses that FreeIMU code. It's really, really terrific code. Unfortunately, it was written by this dude, Fabio Versano, who was a brilliant mind, and kind of had a freak accident and had a heart attack and wound up passing away about a year and a half ago. So he left a great legacy in this code that is now out there, and it works beautifully with this development board, but it's not really being actively maintained, and no one's really taken over the reins. So if I have to challenge you to do one thing, it's go out there and take over Fabio's code, because it's awesome and it needs some TLC. But that's actually the code that I was running on the tall balancing robot that was, it knew which way was down pretty well, right? So it was running that FreeIMU code that turns out to be really terrific. So my laptop isn't hooked up, so I can't actually show you the code. But it's just go take a look. Link in the project or link in the YouTube description down below. Really fantastic, and works quite well. Thankfully, so for this robot, I use this different IMU, right? So I was kind of hesitant at first. You can actually see down here, I put a different IMU on board on it first, the 6DOF. Then halfway through, it was kind of giving me erroneous readings. So I switched to this, which is that all-in-one single chip board. Single chip 9 degree of freedom IMU. So again, it's got the 3 degrees of freedom from the accelerometer, 3 degrees of freedom for the gyro, and 3 degrees of freedom for the magnetometer, which is just a digital compass, so it can actually tell which way is north, or magnetic north. So I use that one, and luckily, back in April, somebody on the internet, I forget his name, somebody awesome on the internet, gave us a pull request that added a bunch more of this kind of fusion algorithm code for this development board. So both of those boards, again, they're inertial measurement units. They are kind of all-in-one motion sensing, direction sensing boards, and there's now really terrific code that's open source that you can go take a look at, look under the hood of, and use.
Yeah, and certainly if you end up taking a look at this FreeIMU code, and if by chance you make it any better, please let us know, and then we'd love to incorporate it in our next version.
We will support you in any way we can. We will send you all the development boards. Yeah, so that's really great code. There's a couple of forks of it. None of them have really taken off. I think there's the Free6IMU is the one that you might find on the builder.org tutorial. It's really good stuff. There's all these people on IRC right now that are, oh, everybody send me development boards. Asterisk might or might not be true. So what do we do with that? So we have this beautiful, clean output, feed it into a PID controller, boom, magic happens and something balances. So I did that, and it turned out to be really complicated. So PIDs are really, like I said, it's the classic algorithm for taking all these inputs, getting one output, feeding it to the motors, and making this thing balance. But I found that it turned out to be a lot more complicated than I was expecting. So I read all the academic papers, all the how to tune PIDs, how to do this. I put up an Instagram on the somewhere on the internet, and it shows the robot balancing really well. And that was actually using a cascading PID algorithm, which was so mind-blowingly complex to me, my poor little brain, that I literally couldn't even. I was so 1,000% done. I couldn't even. So what I did is I Googled it a little bit more, and I found this guy who turns out to be one of my heroes. His name is David P. Anderson, and I think he teaches geology at a university, I think somewhere on the East Coast, maybe Southern Methodist University. And he built a balancing robot he calls NBot. I wish I could show you this little video. I don't know if we do a video camera on a screen over the internet, is that going to break the internet? Nope, different. Oh, actually, same dude, different college. I should have given Mike this video. Sorry, Mike. NBot, I can probably send you a link really quick.
I think I got it.
But he built this little tiny two-wheel balancing robot that is fantastic. Like I said, he calls it NBot. There's a photo of it. If you go to geology.smu.edu/DPA, whatever, it's really.
I sent it out to Tony, so hopefully
cool.
we'll get it.
So take a look at this video. It's awesome. And I noticed, and he built this robot first in I think 2002. And so this robot's been around a long time. So it doesn't. I know it doesn't use any fancy, crazy algorithms. It doesn't use any ARM processors or anything like that. It's got to be bare bones if it was built, over about a dozen years ago, right? So I saw this robot. It's like I need to know how he did that, right? So luckily for us, he is awesome. Like I said, he's one of my heroes. He builds a lot of robots, and so he put the theory of this robot control on the internet in a text file. So if you go to the GitHub repo, it's actually called dpa_nbot.txt. And if you take a look at that, it explains in detail what he was doing to control NBot to make it balance really well. So the way he does that is it's kind of like a dual, instead of a PID controller, it's a dual PD controller. So he just doesn't even use the integral term at all. So it's only the position and the derivative terms. But he uses two of them. The first one is the direct output from the inertial measurement unit. So it knows which angle it's at and how fast its error is accumulating. So the P, the instantaneous angle offset, and the V, right, or the D, so how fast it's actually accumulating error. So that from the inertial measurement unit, as well as from the wheel encoders. So there's a really cool side effect of that. So it uses the wheel position, right, the instantaneous wheel position, and the wheel velocity as well. So those are the four parameters that I wind up tuning with my 4 potentiometers on these robots. So I'm controlling the coefficients for the angle instantaneously, the instantaneous angle, the angle velocity, as well as the wheel position and the wheel velocity, right? So with those 4 things, we can essentially balance our robot. So the cool side effect of that is if you're using the wheel position as an input, it actually doesn't want that to accumulate error, right? So it wants the wheel position to be 0. So as it moves in one direction, it's going to count through those optical encoders. It's going to count maybe 100 clicks, to the left or to the right, back and forth. And then as it accumulates that error, what it wants to do is it wants it to kind of pull it back to 0. So the side effect of that is like when you saw the tall robot balancing, is as it would drift from where it started, it would kind of drift back as well. So as it would accumulate error, it would always come back to where it started, which is a really neat side effect of this particular control structure, control algorithm.
Yeah, the MIP that we showed at the beginning also kind of does that when you turn it on. Kind of just rocks back and forth.
Yep, so and it wants to stay where it started, right? So that's a really, really nice kind of side effect. I think it makes it, it's not a bug. It's a feature, definitely a feature, not a bug. And then from there, I'm not going to, again, I can't show you the code, I'm not going to go into it too much, but the easy way to control the robot from there is to just add an offset. So rather than saying, I want you to stay where you started, you say, hey, go 100 clicks forward, maybe 200 clicks forward, go 1,000 clicks forward, increment it kind of gradually, and then you can actually control the robot. And you can add an offset to one wheel or another wheel, and then you can actually turn the robot really easily. So
this would be good for things like our autonomous vehicle competitions?
Boy, howdy. Would it
Boy,
ever?
howdy.
Yeah, we actually had a couple of self-balancing robots at the AVC last year. So
yeah,
I want to talk to them and see what inertial measurement unit were they using? I don't know.
I wonder.
But yeah, so it'd be super easy. Add an offset, boom, now you're going around a autonomous vehicle course. From there, you can add sensors on the robot, object avoidance. I don't know if Mike pulled up that video. It's just a video of the N-bot kind of going around the basement of the physics room in his university, right? So it's really cool. It's got a little wall sensor, so as it goes along, it might get closer to the wall, then get further away, and it just follows the perimeter of this entire basement. And it's a really fascinating video, and he's using that 4-term algorithm, right? So the angle velocity position, wheel velocity position. Those 4 things muxed together, they're summed together with those coefficients. And that's how that balances. So I don't know, that robot was truly inspiring to me. That's kind of what I modeled a lot of the code on for these robots, as everyone's poking around the GitHub and telling me how bad of a programmer I am. So yeah, so that's just the dual PD control algorithm that I think is really fantastic and should be used. I don't know if it's worth mentioning.
What are these guys? Are these anything?
Oh, I just put these all down just because. Again, I'm really fortunate because I work at SparkFun and I can just like walk about 80 feet that way and get just about anything we have out of stock and just play with it. So it's really nice. So yeah, through that very door. So as I went through several iterations of this robot, the first motor controllers I used were these the little mini moto breakout boards that we have that are really fantastic. I think this is a Mike Horde joint. He put these together. Really fantastic little motor drivers, but they were interfering with the I2C communication from the inertial measurement unit. So it's hard to believe, but that tiny little chip is the motor driver. So I have them two linked together here. I had those on the robot before I switched out to this less expensive motor controller. But yeah, just because I2C doesn't always play well. I think it's 100 kilohertz is the bus clock, and it started interfering with multi-master thing. Yeah, it was really complicated. So I went for the simpler option that used a lot more I/O, but such is life. And in addition, I should mention, just as I kind of play with these things, as I evolve whatever project I'm working on, it's totally okay. That's why I like jumper wires so much, to say, oh, like I started this off with a Pro Mini, which I have here for posterity as well. So I started off with a Pro Mini and realized I didn't have enough interrupt pins for both quadrature encoders. So I swapped it out for the Pro Micro, which has 4 interrupt pins instead of just the 2. You know, totally a fine trade-off to make. The code didn't even have to change. So my projects evolve a lot, which is why I'm such a big fan of jumper wires and breadboards and not making anything permanent until I know it works. So, which comes back to bite me every now and again, but not too bad. Oh, man.
That was a lot.
Yeah. Whew. I need a break.
Yeah. What do you think?
So,
what's next?
Are there any questions from the internet? No questions? No. Yeah, just talking so fast.
We explained all the things.
Just talking so fast, all those PID loops. Check my notes. So just because we're talking about these things, the only downside with that 4-term control algorithm is you need a set angle. So a set target, set point, right? The set angle. And that's why I was so impressed with the MIP, the little self-balancing toy, because it can adjust its center of gravity. It can adjust for center of gravity changes on the fly. Whereas, you know, if this thing were to be balancing right now and I put, you know, some pliers on top of it, the center of gravity would change dramatically and it would just fall over. Whereas, you know, the MIP, I could maybe put those to balance on him, and see, he just kind of figures it out, you know, with all these dynamic changes in the environment, right? So
Needs a hat.
I want pliers for a hat.
Yeah.
Replace my trilby. But yeah, so it's you know, it turns out to be a really, really tricky problem to do that. So one of the ways to get around that, which I'm guessing they're doing in this little device, is with the cascading PID. So in that sort of a situation, you have these 2 PID loops, or 2 PID controllers, and one would be a PID with the wheel speed as an input, and then a target angle as an output. Right, so as you know, if you know the wheels spin really fast forward. So if you know we change the center of gravity, I'm gonna just dark around the thing. So if he was balancing like this, maybe balance. So if he was balancing, when I put the pliers on the front, it's going to change his center of gravity far forward. So he's probably going to run right across the table here. So if I drop these here, so see how he goes forward? And so what's happening is inside, it's using these optical encoders on the wheels to detect that, oh, whoa, I'm going way far forward. You know, I thought I was balanced, something changed, my wheels are going way too fast. So it's actually feeding that into an output that is the target angle that it's trying to hit. So as the center of gravity changes, if I take these off again, oh, he's doing gesture recognition. If I take these off again, he'll go backwards a little bit. And then it'll see those wheels moving real fast, and say, "Oh, something changed. My center of gravity changed." And so that would be your cascading PID. There's some example code for that in the GitHub repo as well, with those cascading PIDs, with the wheel speed as an input and the target angle as an output. So that's I'm guessing that's how they made this MIP. But how did they make this MIP?
I don't know. Should we take it apart?
I think so.
Yeah. He's so cute, but we're gonna take him apart anyway. So yeah, I got one of these last week to play around with, and of course, the first thing we do here at SparkFun is take everything apart. So let's see how this guy works. Actually, the first thing that you're going to need to do is, when you get your MIP, these wheels are actually covered by a piece of plastic. So we just drilled out this hole so you could get to the screws underneath. But once you do that, the rest is simple. You only need one screwdriver, Phillips head. And we're going to start by taking the wheels off. And they just kind of, sort of, there we go. So yeah, just slides right off of there. And then basically the rest is just a two-part chassis plus the head. So this right here is the battery pack. So we'll start by taking that guy out. Don't want to have him turned on. That's actually a great question. What is the battery life? You know, it probably says on their website. I've been running this at least probably 6 or 7 hours so far, and it hasn't died yet. So I imagine it's quite a long time. I don't think it says on the box, but it probably says on their website. So there we go. That's the battery pack. 4 AAA batteries. And then, yeah, we're going to... So the speaker is back here somewhere. And we'll just kind of take this guy apart. Poor guy.
I don't think he minds.
He's taking a lot of abuse this week. We have dogs around here.
Says, I know now why you cry. So the MIP, I think, was developed, like I said, at the robotics lab. I forget the name of it. The robotics lab at UC San Diego by a couple of really smart professors there, and I think a team of graduate students. I'm not entirely sure on that. But it's a really, really great product. They spent, I think, 6 years developing the technology and getting it miniaturized and getting the cost down enough to where they could sell this viably as a toy. And so they partnered with Wowie, the company that does the actual manufacturing, to make it a real product.
Right.
So it's always fun to spend years designing something and then actually being able to go to a Best Buy and buy it off the shelf. So
yeah, exciting. So in case you were wondering, the arms actually don't do anything. They're just solid plastic. That'd be a good hack for one of you out there. So be careful when separating the two parts of the chassis here, because as you'll see, there are some wires that connect to both halves here. So what we see when we take it up, we've got the back of the battery pack here. This is the switch. And what's most interesting to all of you out there is check this out. There's an unpopulated UART. So nicely labeled for us, TX, RX, and ground, which leads me to believe that we ought to be able to do some fun things with this in the future. I believe that they're planning on releasing a developer API. Huawei has done that with several other of their products. So if you're interested in hacking this thing, I would keep an eye on that. I'm sure we'll report it here at SparkFun too. First thing that catches my eye is this guy. This is a low energy Bluetooth module. I sent out the part to Tony, so she should have it. And what's really great is these guys are not like soldered in there, so I'm just gonna take my pliers and let's pop this thing out. And one. And two. Oh, and let's do the speaker while we're at it. Watch me. There we go. So that kind of lets us at least have a clean look at the motor housing here. So what you'll notice is there's two motors and housing. Let's see if we can't pop this out a little bit more. There we go. Okay, so this is the main IC here. It's by a company that I hadn't heard of before I took this apart. I think it's called Nuvo. Anyway, it's from China. It's an ARM Cortex. I think it's their Mini M0 series. Down here we have the sound module. Unfortunately, it's non-rewritable PROM, so no hacking. Yeah, no hacking that. But a lot of what Dave was talking about and what's so impressive about this is the IMU, which is unfortunately glued in right down here. And so we can't really get a good look at it without probably doing some permanent damage, which I'm not quite ready to do to this guy yet. But you can see quadrature wheel encoders right here for the right wheel and right here. They attach very nicely to the board. These are the two motor inputs. And let's see, what else?
How about that motor driver?
Oh yeah, so this is an interesting decision. You'll notice, unlike Dave's mini robot, there's not one H-bridge chip on here. There looks to be quite a few different discrete transistors. I'm not sure what in the design process led them to do that, since H-bridge ICs are pretty cheap these days, but maybe they had a special tuning thingamagic-y
I'm
thing.
sure they had their reasons.
They're smart guys. So, let's see if we can dig a little deeper. So, we have the LED in the front. Let's take that off. Nice little RGB LED. Even has the R, the G, and the B labeled for us. Very nice of them.
Hacker friendly.
And then we've got this stuff going to the headpiece. So let's just do a little lobotomy and see what's in there.
Poor little dude. Kind of feel bad for him. Go all Henry VIII.
Right. Or one of his wives.
Right.
Or Marie Antoinette. Or all sorts of fun historical figures.
Beheading. Glad it's not a thing anymore.
Yeah, really. Almost there. Almost there. Stay on target. Okay. Interesting. So, I'm betting that there are some IR transceivers in here somewhere. This guy. Probably it. Let's see if I can't take off some more screws here.
Let's go deeper.
Always. Leave no screw intact. That's our motto here at SparkFun.
We have a lot of mottos, as it turns out.
Apparently, I just invented that one. So, Looks like this is that would be, my guess is an IR receiver.
Yep.
These guys can do some pretty neat things when you have more than one of them, including play laser tag. So the aim of playing laser tag is to actually hit this target with the eyes of your robot, right, which are IR LEDs. And we can't really get a good look in there. I bet we could probably pry this piece apart if we really wanted to, but I don't know that there's anything that
Is it
interesting.
the IR
going
motion
on.
sensor for gesture recognition?
Indeed, yes. And so, as you may have seen when we swiped our hand in front of it, we can make it turn or go forward or backward. So basically, here we have it. Nice design. It looks pretty hacker friendly. It'll be really interesting to see what they do with it as far as the API and developers go. You could think of some cool things to do with this. Let's see. I'm going to see what happens if we try to take apart the motor housing here.
Gears everywhere.
Yes. I tried to minimize the amount of screws I had to take out, but you know, we want this thing to work.
So this little dude packs a punch for the price. So for $100, it's got, you know, Bluetooth Low Energy. It's got that gesture recognition through the infrared sensors. It's got a speaker. It's got, you know, it's got a lot of functionality, and it self-balances. So you know, it's got that inertial measurement unit. It turns out there's a lot of tech that they packed into this thing for the low retail price of just $99. So I was really excited to get my hands on one of these, and I can't wait to figure out what they do with that UART port. And I want to hack it.
I'm sure you guys could take this apart if you wanted, but you can kind of see they're pretty simple motors. I think what really is the trick here is the quadrature encoders and whatever code they've got running on that ARM chip that does a lot of the programming and PID stuff that Dave was talking about. As you can see, it balanced really well. Straight out of the box, pretty good. It handled me taking it apart at least 3 times and putting it back together. So pretty sturdy, pretty well designed, and I'm quite excited to see what's forthcoming from Wowie about being able to hack into this. So if you guys get your hands on one of these and manage to do something interesting, please let us know.
Coming soon to a SparkFun near you.
What else? Well, if you want to see the speaker, I can take that out.
So now put it back together and make it go again. Okay. Don't cut the green wire.
Yeah, the speaker has a neat little housing. Casey, one of our engineers, was also messing around with one of these and managed to get into the sound card library. And he said there was quite a lot of sounds on this sound card here. All right. There we go. Looks like a 16 ohm, half a watt doohickey. Again, polarity marked. Very nice of them. So you can always hook this speaker up to a sound card of your own and do something fun. But I think that's pretty much it. Of course, if you have questions, let us know in the YouTube comments.
Are we going to do a fully fledged teardown on one of these with high-res photos? I think we're gonna.
We'll definitely have more info on this little guy coming up. Now I'm going to try to put them back together. What do you think?
Yeah, I want to see. I want to see a time lapse of you.
Oh gosh.
So they do pack a punch in those things. So one of the biggest things I learned when just going down this whole road of self-balancing robots and learning the tech and the hardware, the software, I didn't even know what a PID was a couple months ago when I got started in this. So I read a ton, but the biggest lesson I learned, aside from, again, all the manual inputs and outputs you can have, make pretty pictures, draw a graphs, do what you got to do. First thing I did was sit down and draw a free body diagram of the balancing robot itself, right? So, which forces are going to be on it and this and that. Turns out that that's really useful. And if you are smart, smarter than I am, then you can actually figure out which motors would be totally, perfectly linked for your application, right? So for me, it was kind of a little bit of a guess and check, especially on the big balancing robot, which is totally falling over on the ground right now. But I started off with these motors that didn't work very well. Then I got some that were too fast, too slow, and it was kind of a crapshoot for me because I didn't know any better. I was just making it up as I went along. But it turns out that the materials you use have pretty drastic repercussions throughout the entire project. You think, oh, I'll just swap out this piece for that piece. One of the reasons the little guy here doesn't balance so well is the motors just the gearbox is geared too fast. So it's really nice because you can, if I set this down and just let it go, it would go, a couple of feet per second probably, zip across the floor. But it turns out most of the time I just want it to be really precisely controlled, and I don't care how fast it goes. That's why I'm really impressed with the gearbox here in the Wowie, because it has the perfect mix of speed and agility. If you've played with motors before, then you know, your typical DC motor hooked up to a gearbox. If you make a simple Arduino sketch that ramps it maybe from 0 to 255, your 8-bit output, then it might have 20% on the PWM signal before the motor even spins. And then once it starts spinning, it's gonna behave really, really erratically. It'll vary wildly based on the PWM signal. So the actual voltage getting to the motors isn't linear at all, not even a little bit most of the time. So especially with a little toy motor like this. The bigger motors that are on the gearboxes hooked up to the larger robot, those tend to work a little bit better because generally they're faster motors, they're higher voltage, they're hooked up to bigger gearboxes that gear them down a few more steps. So it's you get that fine-tuned control. One of my next steps on the tall guy, I'm not going to abandon this. I'm going to try to find some other Palolo motors to make it more manageable. But I really want to put stepper motors on the tall balancing robot just to make it so I can super precisely control the motors and not have to have encoders, but just get that really good feedback. You get the speed. Turns out to be really useful. I was talking to one of our engineers, Casey, and maybe I'll even use brushless motors if I can go that route, and you get a lot of speed out of them. But that's neither here nor there. Let me say on materials. Yes, swapping out different parts has pretty drastic effects on the overall system. So you swap out a motor, you're gonna have to retune everything. So, and that's why it's so handy to have physical adjustment knobs for tuning your PID. So you can adjust it and see what the effects are in real time. So with that, I think I'm actually going to do that. Just because this little dude doesn't balance doesn't mean we can't learn from him. So we've got these 4 PID tuning knobs. So I'm going to plug this in. I actually have another processing sketch I'm going to run for this dude that does the same thing. It's just that graphed output. Recent, graph MIDI, plug them in, sketch, see if it works. So right now all of the knobs are turned all the way off, right? So what I'm going to try to do is kind of maybe show the effect of each coefficient on that algorithm. So remember there's 4 coefficients. One is the actual angle offset, one is the angle velocity, one is the wheel position, one is the wheel speed, right? So the first one I'm going to tune is the angle offset. So it's not going to work really well, but you can see as I move it that way, the wheels spin to counteract it. As I spin it the other way, the wheels spin the opposite direction. And it varies in amplitude, like the wheels spin faster as the angle increases, right? So, and as the angle decreases, it kind of would potentially rest. So as it goes back and forth, you can make it go really fast. So does that make sense? So that's kind of like the base, it's totally unstable right now. But that's kind of, at its core, that's what it wants to do, is to balance with that. Turns out you can't use only that one term to control this robot. So, that's freaking out. So the other one that I'm going to adjust now is the angle velocity, right? So it's not it's not the absolute position, it's just the, how fast it's moving. This is really useful if your robot is balancing, and I don't know what this says about humanity, but when I first got this thing balancing, I was really excited. It was, took a long time. I had to put the whole thing together, and I'd go show people all over the building. Oh, check it out! I got this balancing robot. 100% of people immediately just slap it. It's like, guys, I spent like months building this thing. It's my pride and joy. I'm really proud of it. I'm super excited about it, and everyone immediately just pushes it. It's like, so what happens though is when people push your robot, it creates a really, that instantaneous, or that rate of change for the angle change, spikes, right? So when they push it, the graph is going to spike, and you'll see what happens. So I'm going to change that value all the way up. Oh, nothing happens because I flatlined. Oh, big boo. Oh goodness.
Why not use stepper motors?
That was exactly. So yeah, one of the questions is why not use stepper motors, and that's exactly what I want to do for that big the tall one. I'll keep talking about it. For this dude, so what I want to do is put stepper motors. I'll see if I can find stepper motors that will mount on the back of this channel. I don't know if there's anything Actibotics. I haven't looked into this just yet, but I'll find some mating for Actibotics, for a stepper motor to go directly into that wheel, and then that way, you don't have to rely quite as much on the optical encoders, because just by driving the stepper motors, you kind of get that positional offset just by driving it, by counting the number of clicks you send to the stepper motor controller. So yeah, steppers would be a terrific idea. That's next on my list for this particular platform. Good question. Go internet. Yeah. Those internet folks, they sure are smart.
And also,
good looking?
Yeah, in your case at least.
Well, come on.
We'll also be adding the links to the various components that we discovered in the MIP on the links on the comments page on YouTube also.
If there's one thing we're really good at here at SparkFun, it's finding data sheets. We can find a data sheet on just about anything. So now, back to this guy, I have that first tuning parameter set pretty much all the way up. So you'll see as I move the robot, so only the act of moving it will change it. So once it's resting, the wheels aren't going to move anymore, right? So unlike the first one, which was a function of the overall offset. So this is just a function of the error in the movement, right? So if I move it fast, the wheels spin really fast. And again, that counteracts, that part of the algorithm counteracts your really good friends who have the best intentions that walk up and just hit your robot. So again, once it sees that spike, there's that spike in the angular momentum, it'll offset that. So with those two combined, you can get a pretty decent algorithm, a pretty decent balancing robot. I haven't figured it out for this guy yet. Again, I think it comes down to those motors not behaving as uniformly as I would like. I'll figure it out. I'll update the code. I'll push it out on the interwebs. So yeah, that's your PD controller. The other, I'm looking at my pretty graphs. Again, you always got to have a pretty graph.
Show us the pretty graph, Dave.
So here, oh buddy. So as I move it back and forth, you can see the angle changes, right? So as it redraws. So as I move it back and forth, you can kind of see if I can get that really pretty sine wave. So and then this one down here is the angular momentum. So if I move it really fast, that's what makes that one spike, right? Ooh, too much spike. Too much spike. Oh, I think I killed it. This IMU is really finicky. I think there's something in the I2C bus that probably my rat's nest of wires here. I can't imagine it's getting a clean clock signal. So next step for this guy is to solder everything to the proto board to make it a lot more resilient to falling forward. This has traveled back and forth quite a few times to my house, and it's starting to die. It needs some solder love.
You still need
Technically, no. So there's the question from the internet is, if you were to use stepper motors instead of a DC motor on a gearbox, would you still need optical encoders? Again, this little robot has the optical encoders built in, so that's how we get our positional feedback on the wheels. If you were using stepper motors, technically no, you wouldn't need the optical encoders. The way a stepper motor works is there's a bunch of coils inside, and so you actually pulse the motor, right? So you actually, if you keep track, you can count how many pulses you've sent to the motor controller, and so you could actually keep track of how far the robot has traveled, right? By counting those pulses, just kind of intrinsically, that's something you would know. It would still be nice to have optical encoders, just because, especially with a stepper, unless you have a really, really fancy motor controller, you're not going to know if it actually made that step or not. And that's kind of the feedback with the DC motor is, you keep upping the voltage, you PWM the motor driver, the H-bridge, and you keep upping the voltage until it starts moving. And only once it starts moving do you know that anything happened at all, right? Because there's no feedback from a DC motor. There isn't that feedback from a stepper motor either. So you can make the good assumption that the motor is moving, but it's always nice to have an optical encoder as well. If you're trying to keep costs down, I know optical encoders can be super expensive, especially the ones that we sell. They're really, really precise. They're machine grade. They're beautiful. They're aluminum. But if you don't want to pay $45 per channel, if you're using a stepper, I would say rely on the counting of the clicks.
There's also like a plus or minus error for most cheap steppers too, on if it says 0.2 centimeters per step or something like that, plus or minus some amount. So if you need real good precision, it's not going to save you any money in the long run to not have the encoders on there.
Yeah.
Sadly.
Yeah, if you're trying to keep your bill of materials down at the lowest cost, then I would definitely recommend steppers. Just go that way. I forgot, I got the bill of materials for this guy down to about $150. There's a link to the wish list if you want to try hacking on this exact platform. Again, I couldn't figure it out in the couple of weeks that I spent hacking on it. I probably put about 10 or 12 hours into building and programming this. I couldn't figure out how to get it to balance. The tall guy I spent probably a month and a half on working, every couple of nights, every other couple of nights or whatever. And it took a long time, understanding all that IMU code. There's a lot out there. But so this guy, I really just wanted to keep the cost low. So if you want to hack on this platform, check out that wish list. Chances are you already have a lot of the stuff. You don't necessarily need to buy a new breadboard or a battery holder if you've got one. Again, the double stick tape, which I brought down here, this is really nice double stick tape. I don't know where we sourced this from, but it's the 3M sticks to anything, will not let go tape. That's what I used to hold the battery pack onto the PCB. This stuff is really nice. $10 a roll, and you only get a couple of meters of it, but man, worth every penny. I was going to reposition the battery holder. No way I'm getting that thing off. Seriously, it's like on there.
Oh, I know.
So I guess Chris, one of our catalog folks, double stuck an Arduino Pro Mini to his desk with this tape, and it's still there. And
will be forever.
And it will be until the dawn of time. There will be supernova, and this Arduino Pro Mini will be stuck to his desk. But yeah, so I based this one again on the Pro Micro. Totally up to you. Different, if you have a different microcontroller you like, if you prefer, use that one. I think I might swap out a Teensy on this board just because I want more interrupt pins. Right now, I only actually have one wheel hooked up to the encoder, or one wheel encoder hooked up to the Pro Micro, just because I ran out of pins on the Pro Micro. You can probably not see, but every pin is pretty much occupied at this point. So you need more real estate. I need more pins, more I/O. Can never have enough. So yeah, that's kind of.
You mentioned the Teensy.
Yeah. I like the
We love
Teensies a lot.
Teensy.
Yeah, plus they're a lot faster. They operate at like 90 megahertz or something like that.
You can overclock them at 96.
Yeah, so you can operate them really fast. This little dude's operating at about 8 megahertz. But the cool thing, even though it's so slow, this is a 3.3 volt Pro Micro, even though it's so slow, that IMU, as it turns out, can spit data out really fast, and 8 megahertz is fast enough. So out of this IMU, you can actually get about 120 hertz. You can get 120 legit samples per second of what your offset is. That's way too fast even for this little balancing robot. I think I have this set to update maybe 50 or 60 times a second, so 50 or 60 hertz. I think the delay is 40 milliseconds, I can't remember. But yeah, so it's more than fast enough for a balancing robot. And that kind of shows how cool these little Atmega chips are. The Atmega 32U4 on the Pro Micro, if I'm not mistaken. A lot of people kind of scoff at them, like, oh, you'll never do anything real with that little microcontroller. Look at your little Arduino, it's so lame. It's like, well,
size doesn't matter.
Yeah, size doesn't matter. And this little 8 megahertz, 3.3 volt thing, something about the motion of the ocean. You know what I mean? So it's more than enough for even a complex project like a self-balancing robot. So it's got a ghost in the machine. The motors keep spinning. Nothing's set up. I don't know. So yeah, the biggest takeaways from this: put knobs on things, look at pretty pictures, draw pretty pictures. It doesn't matter which hardware you use. Just don't be afraid to swap things out. Cool. What should I talk about for 10 minutes?
You can see
Get the nip back. So what I want to do is I want to go see. I want to see how many red boards we can stack up on the MIP.
Yeah. So I'm
It's a toy, right?
coming along here with this guy.
You know what's cool about being at SparkFun production?
What?
People are starting to leave, so I can go pilfer whatever I want out of production. How many red boards do you think I could find?
I think
Dangerous words.
10. So, now that Dave has left me, I'm just going to continue screwing this guy together. I'm almost done. As always, I have more screws than I started with left over. So, you know, leave no screw unscrewed. Is that what I said earlier? It's a motto.
Can I take these for a minute?
I have done this before, but, you know, nothing is certain, especially live on the internet. Find anything good? Or bad? Oh, wow.
Is this on
I've
brand?
vastly underestimated.
I found some red boards.
That's a lot of red boards.
So, like I said, the MIP is a toy. It's a $100 toy packed with a bunch of technology. Again, that Bluetooth low energy, all the little I/O devices. So, but it's got a lot of kind of toy modes. So one of the modes out of the box, it's got I think like 5 different play modes. One of the modes out of the box is the natural thing. The first thing everyone does, like I said, hit it, try to knock it over, for better or for worse. Second thing is how much stuff can we pile on top of it? So the folks at Wowie knew that this is a thing, so they actually shipped it with this tray that we played with a little bit earlier. So this is a tray for the express purpose of seeing how much stuff you can pile on top of it. So as soon as we get this thing back together, I'm gonna put the tray on. I want to see, these are red
All right.
boards. You're familiar with the SparkFun red board? This is a fresh batch. These are just tested, fresh out the oven. So
A little shakier than he was before,
A little shakier.
but operational. I'm just going to tighten a few screws, I think.
Got a screw loose if you know what I mean. It's not the only one.
Present company included.
So another thing I like about the Wowie, just you know, trying to justify my own kind of failure with my little dude here, is that it doesn't, you know, it is an inverted pendulum. It is, you know, kind of naturally not stable, right? Naturally unstable, right? So even with the Wowie, it kind of moves back and forth quite a bit. So there, you know, it doesn't have that PID perfectly tuned to where it will just be solid as a rock, hit and then go, you know, and stay. So no matter what, it's always going to move a few centimeters forward and back as it, you know, tries to find that stability that's never really going to happen. So I guess, you know, if it was on like a deep piled rug, maybe it would, but you know, on a hard top table like this, it's never going to be truly stable. So. And I appreciate that. You know, it lets me know that it's a hard problem. A bunch of people from UC San Diego worked on this thing for 6 years. I'm okay. All right, little buddy.
Well, he's aged a little bit.
I think I aged a little bit today.
So that's the gesture. That still works. That's good.
So I want to take bets. How many do you think we can? I'll bet you a beer at the brewery we can get more than 10.
More than 10.
I think we can get more than 10. I
All right,
don't know
you're
if
on.
these stack. How well do these stack? I should.
Oh, if we get headers.
This could be.
count?
Yeah, this could be trouble.
Oh, you know what I forgot to do? I forgot to rehook up the LED in this chest. Oh well.
That's okay.
I have no idea what mode he's on now.
Can you control the front?
Yeah, here we go. All right,
Cutest little guy.
10 is the bet. Are we shaking on it?
Are we shaking on it? I don't know. What do you think? Think 10? I think 10.
Deal. All right.
Oh.
He's chatty right now. All right, that's 3.
4.
Oh, I don't know, Dave.
I gotta. 4. Oh. Okay. 5.
He lost.
6.
6.
7.
Ooh, getting creative.
8.
9, 10. Oh, wow.
Gotta keep going, gotta keep going, gotta keep going.
12. 12. Look at that. That is amazing. You're good at
So-
Jenga, aren't you?
Oh man, where do I have a beer? So, uh-oh. 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 Come forward, come back, little buddy.
That was at least 13. Production, if you're watching this, we're sorry.
So, but there's a lot of science happening there. So as the center of gravity changes, as we pile the red boards higher and higher and higher, the center of gravity is getting higher as well. So it has to account for that. The little MIP has to account for that. So again, what it's doing is it's actually looking at the wheel speed. So that's where those optical encoders come in so handy. A lot of people do build balancing robots without optical encoders, relying only on the gyroscope or the accelerometer or the fused output. But having the wheel encoders lets you do things like adjust the PID algorithm or algorithms. To account for the center of gravity changes in real time. And if you're pretty clever, if you're good at programming, you can make it pretty good.
I'm trying a different strategy.
Get him away from the box. Oh, too much, too less. These are not
Dave is way better at this
These are not
than
going back into stock, by the way.
Well, we've only got a couple minutes left, so if there's anything that you want to ask us out there, now would be the time.
Go gadget internet.
If any of you are actually curious about inverted pendulum mechanics that Dave schooled you a little bit today, I know I learned something.
I don't know that I learned anything. So
We want it to be what?
that's all I got. So with that, go out
Oh yeah. Wait.
and
It's
buy
Friday?
a MIP. Yeah, so this is kind of a sneak peek of our Friday new product post because the MIP is actually going on sale. We've got a bunch of these in stock. I don't know how many, but a ton of them. And they're going to be on our storefront on Friday. Look for them in the Friday new product post coming up on what? Let's come out on Friday. Friday, weird. Yeah, funny how that works. Thank Greg is our videographer. He's the smartest one here. So yeah.
And this is
Clever
the
dude.
only one I took apart, so the rest should be good.
So yeah, if you buy a red board on Friday as well to go along with your MIP, hope it wasn't demoed today. Yeah, check it out. We have the Friday new product post. It'll be the MIP. It'll be a bunch of other cool gadgets and gizmos as per usual. Because if there's one thing we like at SparkFun, it's gadgets and gizmos aplenty.
And dogs.
And dogs. No more dogs. But yeah, with that, this is SparkFun Live, broadcasting live from our studio
In production.
in production here in Boulder, Colorado.
Oh, one last question.
From Road 8 Park,
Uh-oh.
calling in and wants to know what is the difference between a duck?
What is the difference between a duck? I have a follow-up. I have a return question. How many orange peels does it take to shingle a doghouse? I don't know. No, these are live questions.
42.
42.
All right. Until next
Cool.
time.
Until next time. This has been SparkFun Live.